Good afternoon. Thank you for joining us on our call today. My name is Katarina Ost from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Tool and Techniques for Commissioning and Maintaining PV Systems. This topic is being presented by Will White from Fluke. Will has worked in the renewable energy industry since 2005, first as an installer for a small East Coast solar integrator, then added sales, design, and project management to his skill set. In 2016, he joined the curriculum team at Solar Energy International and focused on updating and developing course content and teaching in person and online for 5 years. His last role was Director of Business Development, helping clients identify training opportunities. In 2022, Will joined Fluke as a solar application specialist, where he supports the renewable energy testing equipment like IV curve tracers, electrical meters, and thermal imaging cameras. We expect today's presentation to last roughly 60 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. Attendance for this seminar qualifies for a NABCEP Education Credit. Please stay for the duration of the webinar if you would like to receive a certificate of completion. Please reach out to me via email. At this time, I'm going to turn the presentation over to Will.
Hey everybody, I'm going to turn my video on here for just a second, say hello so you can see that I am an actual real person. And then we'll go ahead and get into the presentation. So today we're talking about solar installations and how we do testing of solar and what tools we use. We're going to start off by talking about category ratings and how they apply to the tools that we use in the solar industry. We'll do a brief overview of IEC 62446-1, which is testing of photovoltaic systems. And then we're going to go through the solar workflow, and we're going to spend the bulk of our time on that. We're going to go through each step of solar from installation through commissioning and operations and maintenance, and talk about the tests and the tools that are used to perform those tests at each of those steps. So let's first talk about transient voltage. So what's a transient voltage? It's a momentary unwanted spike in voltage, lasts for a very short duration of time. It's usually caused by a motor or other inductive load switching on or off. Could be from an equipment malfunction. A lot of times it comes from the utility, from switching on the utility. If you're in an industrial setting, could be from an industrial speed drive changing, and often comes from lightning strikes as well. Transient voltages are invisible to most tools. Fluke does have some power quality analyzers that are capable of measuring transient voltage spikes, but for most tools you don't usually see that transient spike because they're so short. They're mostly unavoidable, but they can be very dangerous. And this bottom bullet here is the most important one. Transient voltage spikes can cause damage to the equipment. They can actually cause meters to really explode if they're not properly rated for the environment. So it's really important to get a test equipment that is properly rated and can withstand those transient voltage spikes. So how do we know if our test equipment is rated for those environments? First, we need to know what category of environment we are working in, and they go from category 1 to 4. Categories that we most typically see in solar installations are category 4, which is the highest category rating and is the work environment that is closest to the electrical utility. This would be utility meters, transformers, main load centers right at the point of the main disconnect. Then you move into category 3 environments. Category 3 is what the solar array is considered. So this would be things like our distribution panels, some electrical loads within a building, especially in 3-phase systems, can be considered category 3. And then you move to category 2 environments, which are your branch circuits, your point of use outlets, appliances, things like that. So as we're looking at instruments and trying to decide what tool to get, we will need to know what category environment we're working in. And again, solar arrays are considered a category 3 environment. Within the categories, you also have voltage ratings, and we're going to talk about these more in a second. The bottom line is to know what type of environment you're going to be working in and choose a tool that matches that environment. So if you only work on solar arrays that are going to be category 3 environments, then a category 3 rated meter is acceptable. If you often work on service equipment in a category 4 environment, you need to have a meter rated for that environment as well. So once we know the category rating of the environment we're working in, we can check the voltage rating. And voltage can vary depending on what type of task we're doing. In solar installations, we may see up to 600 volts on residential systems on the DC side in the category 3 environment. We'll see up to 1,000 volts on commercial and industrial buildings, and we can even see up to 1,500 volts on utility scale ground mounted projects. The equipment, the test equipment that we're working with really needs to have the category rating for the environment and a voltage rating that is above what the voltage that we're working at. So another thing that we need to think about is that we need to have the test leads that we're using with our meter needs to match the category voltage rating of the meter itself and the environment voltage we're working at. So for example, a 1500 volt rated meter, make sure that you use the 1500 volt rated leads that come with the meter. You might say, well, where would I ever find a situation where I had a 1500 volt meter and only 1000 volt rated leads? It could be that the leads that came with the 1500 volt meter were misplaced or damaged, and someone grabbed some leads off of a different piece of equipment that may not have that same category voltage rating. So it's very important that the leads that you're using match the rating of the test equipment. The voltage rating can be a little misleading, and we got an example here. We've got a category 3,000 volt can withstand up to 8,000 volt transients, where a category 2,000 volt can only withstand up to 6,000 volt transients. So we can see that the change in category rating changes the ability of the test equipment to withstand those transient voltages. That's why it's really important to know what category rating you're going to be working in. It's also important to know that some meters, and this applies mostly in meters that are being imported, often will say that they're rated for a specific voltage. In this example, they might be 1500 volt, ability to measure up to 1500 volts. But when you dig into the specifications, you find that the Cat 3 rating may be less, and sometimes it could be significantly less. You might find a piece of test equipment that says it can measure up to 1500 volts DC, but is really rated only for category 3, 600 volts, or even only 300 volts. In that case, that manufacturer has probably not tested that equipment to the higher category voltage rating, so it's probably not as robust as a piece of equipment that was rated for the full 1500 volts in a category 3 environment. So again, the bottom line, know what category environment you're working in, know what the maximum voltage of the system you're going to be working on is, and make sure you get equipment that matches those ratings. So how can you tell? Any piece of test equipment that is current is going to have the ratings right on it. So here we can see a Fluke meter. This is category 3, 1000 volt rated. They'll often be dual rated. This one can go up to category 4, 600 volts. So this is a good example of a meter that would be really good for commercial and industrial rooftop systems where we may see DC voltages up to 1000 volts, but it's relatively uncommon to see AC voltages on the utility side that are more than 600 volts. Typically, we're going to be working on a 3-phase 480 at the most. So this test equipment would be able to work on that 1000 volt DC system and work on the AC side close to the utility and the meter or the service disconnect up to 600 volts. Now, one thing I want to point out here, this is our Fluke 325 clamp meter. This is category 3, 600 volt rated, really good for residential roof mounted systems that are limited to 600 volts. The 378 that we see here is rated category 3 up to 1000 volts. So we could use that on both residential and commercial and industrial rooftop systems that go up to 1000 volts. And then we have our 393 clamp meter that's rated for category 3, 1500 volts. So this could do residential, commercial, industrial, and utility system, scale systems up to 1500 volts. Now, the size of these pictures is relatively indicative of the size difference of the actual meters themselves. As you go up in category and voltage, the creepage and clearance requirements internally to the device to ensure that it's going to be safe and be able to withstand those transients increases. So the size of the tool goes up. So you can see that the 393 is quite a bit bigger than the 325, but that's because it's designed and built for that higher voltage environment. Another thing to note that you'll often see tools that are listed or designed to a standard or a voltage and category rating. IEC sets the standards for the creepage and clearance in those devices, but it doesn't do any type of testing or inspections to make sure that you actually meet those requirements. So manufacturers will often claim that it's designed to a specific category and voltage rating, but they haven't done any independent verification of that. In order to be UL listed or get a CSA or TUV certification, you have to have a third-party testing agency test your equipment and make sure that it actually complies with the standards. Fluke does this. We have most of our equipment tested by CSA, so you can find those badges right on the test equipment. And here you can see we've got the CSA badge here. And the UL listing is marked right there. So you know that this device has been tested by that third party, in this case CSA, to meet that category rating and the voltage rating. So you know it's going to be safe for those environments. Now let's get into the IEC testing requirements. This is standard 62446-1 for the installation, commissioning, and maintenance of PV systems. Now, here in the United States, the standard is not required. It is a very good guideline. In Europe, this is a statutory requirement, so you have to do the testing to this standard. So it has two different classes. The first class is for safety. So these are going to be tests on the DC side. They're going to be testing the AC side first, ensuring that it meets the requirements there. And then on the DC side, we're going to test that the metal parts in the system are bonded to ground. We're going to test polarity of all the DC circuits to make sure that the positives are actually positives and the negatives are negatives. We'll test open circuit voltage and short circuit current of each PV source circuit. We'll test the functionality of all the components in the system. We'll also do an insulation resistance test on the DC conductors to ensure that those conductors haven't been compromised. Now, the second class of tests in the 62446-1 standard is for performance. And this would be IV curve tracing and analysis of the IV curves to ensure that the modules or strings of modules are working as you would expect them to. All right, now that we've talked about category ratings, voltage ratings, and the IEC standard, let's talk about the solar workflow. And in this presentation, we're going to concentrate on installation, commissioning, and operations and maintenance and the tests that we conduct in each of those stages. So during the installation stage, specifically for wire installation, we're going to do insulation resistance testing. And this is to verify that as the insulation was being installed, that it wasn't compromised, there's no damage to the insulation that's connected to ground. We can also use it to identify ground faults, which we'll talk a little bit more in the operations and maintenance stage. So an insulation resistance tester sends a high voltage through the conductor. The conductor has to be separated from any electrical equipment. Usually we cap one end of the conductor, and then at the other end of the conductor we connect it to our meter, and then the other terminal on our meter or probe on our meter connects to ground. And it's sending that high voltage through the conductor and seeing if there's any current leaking to ground. If there is, then we know that there's an issue with that conductor and we need to repair that. There's a couple different tools you can use to do this test. The Fluke 1587FC insulation multimeter can do this test. We also have the SMFT 1000, which is the solar multifunction tool, which has insulation resistance testing built into it as well. And the SMFT is a little different than our standard insulation testers. The standard testers aren't designed to work with circuits that have voltage present. There is a process where you can use them to test PV circuits with modules in it. The SMFT1000, however, is designed specifically for use with solar. So what it will do in one of the insulation test functions is it will actually bond it'll short circuit the positive and negative of the PV circuit together and form that short circuit, that closed circuit, and then it will insulation resistance test that closed circuit. So a little bit of an advantage there. During commissioning, we're also going to test voltage and polarity before we turn the system on. We're going to make sure that the system is wired properly. If you have too much voltage, that usually means that they put too many modules in the string of modules, so they connected too many positives to negatives. If the voltage is low, that usually means you have too few modules in series. We also really need to test polarity, especially in a box like we see in this picture. This is a large commercial combiner box. If the positive is landed in the negative bus bar or the negative is landed on the positive bus bar, we can create several different problems. You can have essentially strings of modules that are run in parallel, so they end up being double the voltage of what they should be. So if you turn that onto your inverter, you can damage the inverter there. If it's landed to the negative bus bar, you can actually have closed circuits there where current, short circuit current is circulating through that circuit, which would also be a safety hazard. We can use many different tools to do this voltage and polarity testing. Any digital multimeter or clamp meter that's rated for the category and the system voltage would be appropriate. In our catalog, we have the Fluke 393 FC clamp meter, which is the one that you can see this technician using there. We have two Amprobe multimeters that are rated for 1500 volts. That's the HD 160C and 110C. And then our SMFT 1000 will also test for both short circuit current, open circuit voltage, and polarity. And one thing I did want to point out with the 393 clamp meter, it has reverse polarity indicator on it. So it doesn't just give you the negative in front of the number, which is sometimes hard to see, especially when you're doing a repetitive task and it's out in the bright sunlight, you might miss that little minus. So with the 393 clamp meter, when you have negative polarity, you get the negative symbol on the display as you would with any other meter, but the display also will beep repeatedly for 10 seconds. You will see a polarity word will come up on the display and the display itself turns red. So it's really hard to miss that reverse polarity with the 393 clamp meter. So it's a really good clamp meter to use in solar for those repetitive polarity tests. Another thing we often see in commissioning is IV curve testing to set a baseline. IV curve test measures between short circuit current and open circuit voltage and measures many points along the difference between those two and creates a curve. So you can see some issues there that you wouldn't be able to see if you're just doing voltage or current testing. In commissioning, we'll often see IV curve tests used to create a baseline that you can use for historical comparison. So you can go back and ensure that the system was operating properly when you installed it. Any IV curve tracer or multifunction tool with IV curve tracing is going to work. Again, needs to be rated for the voltage in the category rating for the environment you're working in, and needs to have a current rating appropriate for what you're testing as well. The Fluke SMFT 1000 is 1000 volt rated and it can measure up to 20 amps. So it'll do a string of modules up to 1000 volts, and usually a single string of modules is going to be less than that 20 amp limit. And you can see on the picture here, that's the IV curve right there. And this has got a, that green curve there is actually the plus minus 5% of what we expect. So you can very easily see if the IV curve trace passes the test when you're using that tool. Okay, now that we are continuing through commissioning, we're going to do some ground resistance testing. This is measuring to ensure that our equipment is bonded to the ground rod. It ensures that those non-current carrying metal parts like our module frames, our array racking, metal conduit, that's all bonded to ground. If it's not bonded to ground and it becomes energized, it could be a safety hazard, and it's definitely a safety hazard. So we want to make sure that those metal parts are connected to the ground. So any ground faults have a place to go as opposed to going through the technician themselves if they happen to touch that bonded metal or unbonded metal parts. Fluke makes a couple of products that's good for this, the 1630 ground bond tester and the 1625-2. They can both be used to conduct different ground bonding tests. When we're doing commissioning, we're also looking to do some performance testing, and we want to see if our measured power is equal to what we would expect. We can also use it to measure inverter efficiency and seeing how well the inverter is converting that DC power to AC. This is going to make sure that the system's working properly, and it's going to set a baseline for the future. You can do this with some handheld meters. The Fluke 393 clamp meter can measure DC power, so it'll measure voltage and current at the same time, and it'll actually give you the power output. The SMFT 1000 will also measure voltage and current at the same time. And what you can do is measure voltage and current on the DC side. It will do the power calculation, and then you move the meter over to the AC side and measure the current and power output on the AC side, and it will use those to calculate inverter efficiency. And it can be used on single phase and 3-phase inverters as well. Through commissioning and into operations and maintenance, we often do thermal imaging, and we can use it for a bunch of different purposes. When we're looking for electrical equipment, we can use this on our disconnects, our combiner boxes, inverters, transformers, really any piece of electrical equipment. We're also using it on modules, and that could be aerial thermography or with a handheld thermal camera like we see in the picture here. We can also use it on module interconnects. When we're doing thermal imaging, we want to make sure that the system is operating at a relatively high level, and that's to make sure that the equipment is actually heating up a little bit so we can see that differential in temperature. Thermal imaging testing does require a bit of training to be able to do it well. There are some nuances to thermal imaging that requires that training. One thing I want to point out in this picture, we can see in the thermal image here that this fuse on the left-hand side is a little cooler than the other two. That could be because there's less current running through it, or it could be because it's a different kind of fuse. Not sure what the reason is there, but it might be worth investigating more clearly. We can also see in the scale here, and this is one of those things where training comes important. There's looks like about a 30-degree differential there between the hottest parts and the coolest parts. So there is quite a bit of temperature differential there. When we see hot equipment in thermal imaging, especially when compared to other types of other pieces of equipment, that typically indicates either increased resistance. In our modules, it would indicate that a module is not operating. Modules that are operating work cooler than modules that aren't, because the modules that don't have the power going somewhere, the electrons don't have anywhere to go, so they release some of their energy as heat. Cool equipment usually means that there's either low current or no current flowing through it. We can see here in this picture on the right, we've got the thermal image on the top, the visual image at the bottom, that those circuits are cold, and that the reason being that there is actually no circuit connected to that terminal there. So obviously we're not going to have anything flowing through there if there's no circuit connected to it. But if that had been in one of the other circuits, we would know that maybe there's damage somewhere, or it's not operating for some reason. When we're doing commissioning, we're setting a baseline with the thermal imaging, making sure that we have that available for the future so that we can refer to it and see if anything has changed over time. Aerial thermal cameras attached to either a drone or a fixed-wing aircraft. At this point, drone-based thermal imaging is relatively common. We can also use handheld cameras, which is most frequently used on our electrical equipment, although we can use it on modules and module interconnects as well. Now, when we get into operations and maintenance, typically the first thing when we do operations and maintenance is a visual inspection. We're going to walk around, see if there's anything that really sticks out. It's very easy to see things like burnt out connectors or module damage that is really visible. It's nice to have a checklist. This checklist on the screen here is in our SMFT 1000. That's based on that 62446-1 IEC standard. And having a trained inspector is really important. They need to know what they're looking for, when signs of damage has occurred, and when to flag that for future future inspection and root cause analysis. Okay, when we get into inverters and transformers, they need operations and maintenance as well. We're gonna measure DC voltage and current, AC voltage and current. We can check the continuity of fuses. We'll often do thermal imaging on inverters and transformers to ensure that they're working properly. Torquing terminals is really important. Terminals should be torqued when the system is installed. That should be part of the commissioning process as well as checking those terminal torques. If terminals are under torqued, you can have high resistance connections. High resistance leads to heat, and heat eventually leads to fire. You can also test inverter efficiency at that point, and we can do AC power quality analysis as well. We're looking for variances in voltage, frequency, and any kind of harmonics that might influence the operation of the inverter. One thing I want to point out here, this is a technician using our SMFT 1000. This may look like an odd installation to those of us who work in the United States, but this is a commercial installation in Europe. So they have different code requirements there, and using conduit is not a requirement there. So that's why we see all those conductors hanging out at the back, the bottom of the inverter there. We're doing operations and maintenance of our inverters and transformers to make sure everything's working properly, operating efficiently. It's required in many cases to uphold the manufacturer's warranty. If you don't do the operations and maintenance on a lot of inverters or transformers, you may void that warranty. We're obviously preventing future failures and maximizing our system production, making sure that the system is working efficiently and producing as much power as it can to maximize the financial return for our customers. We use a suite of different tools when doing operations and maintenance on inverter transformers, digital multimeters, clamp meters, our torque tools, multifunction testers if we're doing IV curve testing of our inverters. We again stress this over and over, but it's really important to ensure that we have tools that are rated for the category, environment that we're working in, and the voltage of the equipment that we're working in. We also need to know that if we're working on transformers that are on the utility side of the inverter, that's most definitely a category 4 environment. So we need to make sure that we've got the appropriately rated test tools there. We can occasionally run into harmonic issues on the AC side of the inverter. It's not typically caused by the inverter itself. It may be caused by equipment in an industrial setting, or it may come from the utility. We have power quality analyzers that will hook up to that 3-phase AC connection, and we'll be able to identify harmonics issues. It can also find issues with voltage and frequency as well. Inverters have an operating voltage window and an operating frequency window. So if the utility connection goes outside that window, our inverter is going to shut down. And obviously we're not going to be able to produce any power if the inverter is off. These power quality analyzers can also be used to study loads. So we can identify loads that could be potential candidates for efficiency upgrades. And these power quality analyzers can measure up to 5 times a second or every 200 milliseconds. The higher end ones will also be able to see those transient voltage spikes as well. So if we're getting frequent voltage spikes, we can identify those with a power quality analyzer. Modules are one of the main sources of problems when we get into the operations and maintenance stage of the operational life of our system. Visual inspection is the first place to start. It's very easy to see burnt out connectors. It's easy to see cells that have damage that has led to browning of the back sheet, or we can even see it sometimes on the front of the module. Broken glass, obviously, they're very easy to see. Loose or damaged connectors, that can be hit or miss. You may be able to see those easily, especially if it's a burnt out connector. Ones that are loose or have some internal damage may be more challenging to see. And that's where thermal imaging comes in well. And we'll see a picture of a connector with a thermal image in a minute here. Could be aerial thermography. That's really popular these days, especially for larger utility scale projects, to do a drone flyover and take thermal images of the entire array. That's a very easy way to identify modules or strings of modules that are having issues. And then you can go to that location and do further testing with either voltage, current, IV curve testing, insulation resistance testing, diode testing to identify what the cause of that thermal anomaly is. Mentioned before, any module or module cell that's not operating is going to be hotter than the comparable modules. In the picture here, we see we've got a hot spot on this cell, so most likely either an internal issue with the cell manufacturer's defect, or it may be even shading. There could be bird poop on that cell, and that's causing it to heat up because of increased resistance there. And we can see both the front and the back side of that module. You can very easily identify that hotspot there. Okay, other module tests we can do voltage and current testing. Open circuit voltage testing can often identify issues with bypass diodes. Typically modules either have 3 or 6 bypass diodes, although module technology is changing quite rapidly, so there are other variances in the field. But by doing this open circuit voltage testing, if you have a bypass diode that is operating in a module that has 3 bypass diodes, you'll see a third less voltage than you would typically expect. You can do maximum power current testing with the system operating. That is a good way to see if a module string is actually working or not. This technician measuring current there in that string of modules, and if you look closely on that 393 meter, he's getting 0 amps, so that string of modules is not working at all. Now, we can also do current testing for circuits before we're going to open any non-load break rated disconnects, and we see these quite frequently in solar. This would be your module interconnects, your MC4 or other type of connectors are not load break rated. Same thing with the touch safe fuse holders in inverters and combiner boxes. Those are not meant to be opened under load. So we can use our clamp meter to ensure that there's no current flowing through that circuit before we open up those connectors. If you open those connectors with a load on them, you're going to pull a DC arc. We call it letting the sun out. It's kind of a joke, but that DC arc is not only going to damage the equipment, but it is also a pretty significant safety hazard. So make sure you're testing for current before you're opening any non-load break rated disconnects. Now, when we're doing our inspections of modules, visual inspections are really good. Having a checklist is really nice to ensure that you don't miss any of the steps involved in doing that test. Here we can see a clamp meter that is measuring voltage and current at the same time. We can also change that to power, so it's telling us the volt amps there. So that's producing 44 volt amps, or in this case, DC watts and volt amps are the same because there's no power factor in DC, so producing 44 watts. We can do drone inspections or handheld inspections. Drones are going to be faster for larger arrays, but handheld inspections will work well. Checking voltage and current. You just need a properly rated meter. Never test current in a PV array with an inline current measurement device, so that would be using your probes on a meter. We're always going to want to use a clamp meter. Not many meters are rated for the current levels that we're working at in solar. So if you try measuring current with the probes of your multimeter or even with a clamp meter, using those probes is essentially short circuiting that PV string, and most meters are not rated for that current level. At most they're rated for 10 amps. So at least you're gonna blow the fuse of the meter in many cases, and at worst you're gonna cause damage to the meter, which is could be pretty severe safety hazard to the person holding the meter. If we're working on our arrays, we want to make sure that we've got that category 3 rating at a voltage that's greater than whatever our maximum array voltage is. All right, moving on to talking about ground faults. This is one of the most common issues we see in operations and maintenance. There's a way to do voltage testing on our strings of modules to identify where the ground fault is located within a string of modules. We're going to need to test the positive to negative to measure the open circuit voltage of the string of modules. Then we'll test from positive to ground and negative to ground and see if there's anything there. When testing from positive or negative to ground, you should get 0 volts. On most inverters, when the array is disconnected from the inverter, if you've got a combiner box that disconnects both the positive and the negative, or if you shut down your inverter and remove the ground fault protection device fuse, or if you have a non-isolated inverter that those inverters, the array is not grounded when the inverter is off. So there should be, in most cases, no reference to ground from positive or negative. So when you test from the positive or negative to ground, there should be no volts. You may initially see some voltage. This is called ghost voltage, but that will bleed off pretty quickly. And what we're really looking for is true voltage, not the ghost voltage. We can also do insulation resistance testing to identify ground faults. This is a really good way to identify strings of modules that have intermittent ground faults. They're faults that don't have a hard connection to whatever metal that they're grounding to. Could be because it's a wire that's been rubbing against the racking or the module frame, and it really only gets continuity to ground when it's wet. That's a pretty frequent problem. Another one is maybe the wire gets pinched by a tracking array, and it only gets pinched at certain times of the day. Insulation resistance testing is a way to identify a lot of those intermittent ground faults. You can often find when you're doing insulation resistance testing on PV strings that the IEC standard, I believe, is 1 mega ohm for most voltage strings. You may find that you have a string where it passes the testing standard threshold, but it's less resistance to ground than other strings, so you have an outlier, and that may need additional investigation. I had a situation once where I was doing insulation testing on a flat rooftop system, and one string had a passing resistance. It was above 1 mega ohm, but it was lower than all the other strings in the system. And I went out and found where the string was and found a module interconnection. The quick connectors between 2 modules was actually laying in a puddle on the roof. They had pretty poor wire management on that system. So as soon as I removed that connector from the puddle and dried it off and fixed it properly to the array, the insulation resistance of that string went up very quickly. Okay, let's move on to talk more about ground faults. Ground faults can definitely create a safety hazard. That would mean there's current flowing through energized metal parts. Could also be a fire hazard depending on the situation, because ground faults are often also arc faults where there's a DC arc there. We've seen ground faults on roof-mounted arrays caused by squirrels, where the squirrels have nested under the array, eaten the wire, and the wire caused a DC arc, which then caught the nesting material on fire. And that obviously, no one wants a fire underneath their modules on their roof. So it also reduces system production. If you have a inverter that has a ground fault detection device, which all inverters do, if that ground fault detection device trips and the inverter goes offline, obviously you're going to be losing system production. So we have a couple of different tools we can use to identify ground faults. Our multimeters and clamp meters for testing voltage, and we can also use our insulation resistance testers. And now I want to go through an illustration of the process of testing voltage on the PV string to identify those ground faults. So we have a string of 16 modules here. They have an open circuit voltage of 53.82 volts. So if I take my properly rated meter, this is a Fluke 87.5 meter, that's 1,000 volt rated, category 3. I'm gonna put my black probe, the negative probe, on the negative end of the string, put my red probe on the positive end of the string and measure between the two, and I get open circuit voltage of 861.12 volts, which happens to be 53.82 times 16. So I got the appropriate open circuit voltage there, which you would commonly see on a string. Now if I take my meter and connect my black probe to ground, I connect my red probe to the positive and measure, and here I would be expecting 0 volts, but I'm actually getting a little more than 645 volts there, so I'm gonna write that down and record that measurement so I have it for later reference. If I go to the negative side, hook my negative lead to the negative terminal of the end of the string, put my positive to ground, measure there, I get 215.28 volts. Again, I would be expecting 0 there, so I'm going to record that measurement and analyze it further. So when I go and take these readings, if I took my 861 volts, divided it by the open circuit voltage of the module, 53.82, I get a module count of 16. So that's my full string open circuit voltage was what I would be expecting. When I take the measurement of positive to ground, 645.84, divide that by the module open circuit voltage, I get 12 modules. When I take the negative to ground reading, 215.28 volts, divide that by the open circuit voltage of the module, I get 4 volts. So now I know that the ground fault is between the 4th and the 5th module because I have 4 modules on one side of the ground fault and 12 modules on the other. So I've located that ground fault. It's going to be somewhere here in the circuit between these 4th and 5th modules. So now what I need to do is go out to the array, figure out where that string of modules are, figure out where the 4th and the 5th modules are, and figure out what the problem with this wire lead is. It could be pinched underneath the rack in the module. It could be rubbing against the racking. Squirrel could have eaten the insulation, many different reasons that ground fault could be there. Now I'd need to repair that ground fault. Now I'm going to go through just a really short example of a somewhat common situation when we're doing this testing procedure. I tested between positive to negative, got the same 861.12 volts, which is the open circuit voltage of the string of modules. That's what I expected. I test from positive to ground, got 0 volts. Great, that's what I expect. I tested negative to ground and I got 861.12 volts. That indicates that the ground fault is on the home run and the negative side because all 16 modules are on that side of the ground fault. This is actually relatively easy to miss because your brain, as you're going through testing, you're expecting to see either the open circuit voltage of the string or 0. So it's very easy as you're going through this test procedure to see, oh, 816, yeah, that's fine, and keep going. When actually there is a ground fault there. So if you come into this situation, just be aware that if you see full voltage to ground between either the positive conductor to ground or negative conductor to ground, if you see that full open circuit voltage of the string, then your ground fault is in that home run wire. Those tend to be a little more difficult to identify because those home runs tend to be longer than the module interconnections. But again, you got to get into the array, figure out where that ground fault is located and repair it. Okay, moving on to arc faults. Arc faults come in 2 different categories. There are series arc faults and parallel arc faults. They are a series arc fault is high resistance between 2 connections that should have low resistance. This module interconnection is a good example for that. We want low resistance when our 2 modules are plugged together. If we have high resistance there, it's going to eventually lead to an arc fault. That arc fault will eventually burn itself out, so you can look for burn damage there. A lot of times, those high resistance arcing connections in a connector aren't easy to see visually, so we need that thermal imaging camera. And what we're looking for here is comparing the temperature between different connections. So we're looking for anomalies there, not necessarily a certain temperature actual number. We're looking for differences in temperatures between connections. Parallel arc faults are arc faults between two conductors that should have high resistance. So in this case, a positive and a negative bonding together when they shouldn't be. That would be an example of a parallel arc fault. Again, we can use thermal imaging cameras to detect those high resistance connections. A lot of times the inverter will have arc fault detection and will have a fault code. In that case, one strategy for isolating where the arc fault is to isolate all the strings in the system, turn one string on, so connect one string to the inverter, restart the inverter, see if it kicks up with the arc fault code, and then if that doesn't go through it, maybe you split it in half, so isolate half the strings and then turn the inverter on, see if it still has the fault code. If it didn't, then remove those half strings from the connection to the inverter and reconnect the other half, and you can kind of track it down there. That's kind of the best, one of the best ways to find an arc fault at this point. Arc faults are a serious safety hazard, especially series arc faults. High resistant connections, high resistance leads to heat, heat leads to fire. On this picture, this is a roof-mounted system, a commercial roof-mounted system where they had an arc fault, and it may be hard to see in this, but this is a quick connection between two modules, and this module connector was not seated into the other module connector. So they weren't put together properly, so the high resistance arc fault there, which eventually caused a fire. Parallel arc faults and series arc faults are going to continue until the circuit is disconnected or they basically burn themselves out. Thermal imaging cameras are really good there. The troubleshooting workflow that I just kind of discussed is another option as well. We also need to document these tests. So when we're going through and doing these tests, especially on the commissioning side, we want to record the results so that we can set that baseline and refer to them in the future so that we can see things change over time. A lot of companies are using IV curve testing at commissioning, and then annually they're IV curve testing a select group of modules to track module degradation over time. So having that recorded data, you can see things change over time. To get your technicians to record data, it's got to be easy to record. It's got to be easy to put that into whatever system you're using, and it's got to be easy to get that data out. And of course, it has to be accurate. If you don't have accurate data, it's a garbage in, garbage out kind of a scenario. So we need good data going into a place that's easy to put the data into the system, easy to get the data out of the system, and easy to compare. I'm a really big fan of workflows. Having workflows are going to ensure that you're getting consistent results, especially when you have new people coming on. So if I can provide them with a standard operating procedure, a checklist, a device that has a checklist built in, like the SMFT 1000, it's going to be easier for them to make sure that they're covering all the points as they're working through their job. Test equipment also needs to be calibrated. Usually it requires annual calibration. You can send them back to the manufacturer. Fluke does calibration. This is a picture of one of our calibrators, and they're calibrating a clamp meter in that picture there. Some operations and maintenance contracts may require a certificate of calibration before the contract is executed. So they're going to want to know that you're using tools that are properly calibrated before you go out and do any kind of testing. So keep an eye out for that. Make sure that you're keeping current calibration certificates. So to kind of wrap things up here, all of our test tools are going to have a category and a voltage rating. We need to make sure that those are appropriate for the environment that we're working in and the voltage rating of the system that we're working on. And here you can see this technician using the SMFT 1000. That's a category 3 environment by definition, since it's a solar array, and this is a 1000 volt or less system. We get a bunch of different tools that we need when we're doing it in solar. When I was working in the field, I had 3 tool bags. I had one for my hand tools, one for my ratchets and wrenches, and then a bag just for test equipment. So having the right tool is really important, and it makes the job go a lot faster and safer. That's really important. calibrating your tools, making sure they're accurate so that you're getting good measurements and taking good tests is really important. And of course, wear the correct personal protective equipment and use it properly when you're doing testing. This technician working in a combiner box, it's got live circuits in it, so they've got their electrically rated gloves, they've got an R-flash face shield with the balaclava underneath, and their fire-resistant clothing as well. So the type of personal protective equipment that you're going to need is going to vary based on the test that you're doing, the equipment that you're working on, the overcurrent protection devices in the circuits, how close you are to the utility. It's all going to vary site by site, and even equipment by equipment. And we even find especially when it comes to arc flash hazards, an inverter in one location may have a different arc flash hazard rating than the same inverter in a different location. A lot of that depends on distance from the utility and the speed at which the overcurrent protection devices will activate. So that's the end of the presentation. I'm going to take some time for questions now. And if you have questions specifically for Fluke tools, Katarina's email is there. And you can also visit either solar.fluke.com or the Transcat website. They have a Fluke specific landing page as well. So Katarina, do we have any questions?
Yes, thank you, Will. We do have one question. You have talked about operational limits of the multimeter. Using a multimeter at a temperature below equipment limit can cause what kind of issue? Example, if used below -20 degrees, does it cause only bad reading?
Wow, that is an excellent question that I have not gotten before. Yeah, I mean that's a hard one to answer. I can, if you email that to Katarina, your contact information, I can get you a more specific answer. But my kind of off the cuff answer would be look at the specification sheet for the test equipment that you're using. It's going to have an operational temperature limit that's going to vary based on the type of equipment. I'm not sure what impact the temperature actually has on the test equipment, so I'll have to get back to you on that one. But that's a good question.
Okay, we did get another one. Can you use the SMFT 1000 on 1500 volt utility scale systems?
That's a great question. So the SMFT 1000 rated for 1000 volts at 20 amps. You can use it on utility scale 1500 volt systems with some limitations. If you're doing module level testing, so where you're only testing one module, which we see people do a lot when they're doing that module degradation testing, that's fine. Most modules have a voltage rating somewhere around 40 or 50 volts, much below that 1000 volt rating of the SMFT. If you're testing a 1500 volt string, what you can do is actually split the string in half. So you're reducing that voltage and getting it below that 1000 volt threshold. So that is a way to use the SMFT 1000 on a 1500 volt string. We will also be having a 1500 volt version coming out at some time in the future at a point that is yet to be determined.
Okay, I did get another one another one. On the O&M inspection, you mentioned checking the torque. Are we just making sure it was marked or physically retorquing?
That's a good question. I mean, it's going to depend on the standard operating procedures of your employer or the company that you're working for. I mean, I would say you see, yeah, you've got the torque, the torque marks on there. Assuming that they did the torquing right in the first place, that would be pretty good. I mean, I personally would go through and retorque everything. Most inverter or equipment manufacturers are going to give you some type of indication of how often they need to be retorqued. You know, we've got these things going through thermal cycles, so heating up, cooling down, especially as they're in somewhat harsh environments. So retorquing those terminals is always a good idea. Now, the problem I've always had, and I haven't figured out a solution to, is how to identify over torquing. That's really hard to do because you don't really have a reverse torque meter, and you don't want to continue to torque something past its torque setting if it's already over torqued. So that's a challenge that I've not yet found a solution to.
Okay. What test methods do you recommend to identify loose or improper electrical connections other than DLRO?
I don't know what DLRL is, but yeah, the thermal imaging is the go-to for sure. You're gonna find over-torqued or under-torqued terminals typically have higher resistance, under-torqued terminals especially. But what happens when you over-torque a terminal, and this is specifically to wire terminals, when you over-torque a wire terminal, it puts too much pressure on the wire, and the metal of the wire will actually flow out from behind the terminal, and then it ends up being a loose terminal. So those loose connections will show up as high resistance, so they'll be hotter than other terminals. So using a thermal imaging camera to identify those discrepancies and anomalies in temperature is a really good way to find them. Other than that, I mean, if you've got a really high resistance connection, you're going to see burn marks or indications of arcing. That's a good way to, I mean, hopefully it hasn't gotten to that point, but that's why we do operations and maintenance. We do have acoustical imaging cameras, which is something that you don't see a lot in solar, but they're used a lot on substations to identify arcing. It actually uses an array of microphones, and it picks up certain frequencies and then gives you a visual image very, very similar to a thermal image where it identifies where that acoustical signature is coming from. They use a lot in process equipment as well. But we'll start, I think we're going to start to see those used more frequently in solar. We just haven't yet. Okay, any more?
It doesn't seem like that is the case.
We got a couple more minutes left, so if you get more questions, feel free to pop them in the chat.
Here's one. Doesn't the 1500 volt meter come with 1500 volt rated test leads? How would you end up with leads that didn't match the 1500 volt rating?
Yeah, it does. Yeah, the 393 does come with the 1500 volt rated test leads. And I kind of touched on this in the presentation. The most common way is someone misplaced the test leads or damaged the test leads that came with the 1500 volt rated meter and just grabbed some leads that happen to be sitting around. So if you're working in 1500 volt environment, you're going to want to make sure that you've got the 1500 volt test leads. Another thing to point out that I didn't mention, everybody who has worked with a multimeter before knows the test lead, the probes come with a little plastic cap that you can remove. But a lot of people don't realize that when you remove that plastic cap, it changes the category and voltage rating of the test leads. And it also makes it much easier to arc between test lead terminals. So please make sure that you don't take those off unless you really have to and don't lose them. Fluke has a set of test leads. They're 1000 volt rated that has the little cap part is integrated into the test leads, and you actually turn a little piece on the front of the test lead and it pulls that cap back, so you can't physically lose them. That's a really great option for testing in the field.
Okay,
Right.
Does anyone else have any other questions?
I got time for one more if there's any more questions out there. All right, well, thank you all for joining us, and Katerina will follow up with an email, and if anything else to add there?
Yes, so yeah, if you would like to receive the NABCEP Education Credit, please reach out to me via email to receive the certificate of completion. To find out more about Transcat's product and service offerings, please contact us at 800-828-1470 or on the web at transcat.com. Thank you for joining us today. We hope you got something out of today's presentation and that you continue to join us in the future Transcat e-learning webinars.
Great. Thank you. Have a great day, everybody.
Thank you. Bye.